Okay, in today's video, we're going to be talking about a subject called related rates, which is yet another application of the chain rule. But what's different than related rates and what we talked about before, implicit differentiation, where implicit differentiation lets us figure out how we can find the slope of an implicitly defined function at any given x and y point, which is very useful. I would say related rates is a little bit more of a real-world application of the chain rule. And what we're doing in related rates problems is we're saying, okay, let's say we have a system that has all these variables in it. If one variable is changing at a certain rate, how does that affect the rate at which other variables in the system change? So related rates problems are generally not liked very much by calculus students. I think it's because they're always given in word problems. However, there's a pretty straightforward strategy to solve them. And the biggest thing in the related rates problems is really how you set up the problem and how you decipher what a word problem is, what information a word problem is telling you as it pertains to calculus. Okay, so that's what we're going to be working on. So let's look at this problem right here. We have a 13-foot ladder is leaning against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. How fast is the top of the ladder sliding down the wall at this moment? So you might look at this and get freaked out because you see a word problem and you have no idea what's going on. But the trick to understanding these word problems is first, and you must do this every single time. If you do not do this, you are going to be sorry when you try to solve these problems, okay? Not many people are good enough to be able to solve these problems in their head. In fact, almost no one is good enough to solve these in their head. So what you got to do is you got to get some help. You got to draw a picture. When you draw a picture of what the problem is talking about, it really helps you visualize and understand what's going on a lot better. So let's draw a picture. We got a wall, and we got the ground, and we have a ladder that's leaning up against the wall and touching the ground. Okay? So now we got that. Now let's look at some of the information given. We have a 13-foot ladder. Okay? So we might come here and say, all right, well, we know that this ladder has a length, which I will call L, which is 13 feet. Okay? Now think about this. Is the length of that ladder ever going to change? No. If you extend a ladder to a certain point and it slides down that wall, the length of the ladder is never going to change. It's always going to be the same. So we will say in this case L, 13 feet, is a constant. All right? Now what else do we have? We have the base starts to slide away. By the time the base is 12 feet from the house, it's moving at a rate of 5 feet per second. So let's first look at that thing I underlined. When the base is 12 feet from the house. So as this ladder slides down, the base is going to slide out this way, and the top is going to slide down. So, unlike the length of the ladder, which was a constant, the distance between the ladder and the wall, or the base of essentially, distance between the base of the ladder and the wall, that's going to be something that we will call a variable. It's something that changes with time. So we will call that x of t, okay? Because it's a function of time. At different times, the length of the distance between the wall and the base is going to change. So therefore, if x of t can change with respect to time, what does this arrow that we just drew to the right of the base of our ladder represent? That represents the rate at which that base is changing, or we might call that dx dt. Remember what a derivative means. It is an instantaneous rate of change, okay? So if the base is changing at every instant, the instantaneous rate of change of that will just be the derivative of that base function, in this case with respect to time, okay? So we know that the base is moving at a rate of 5 feet per second. So again, seeing even the units feet per second, that is also a rate. What does that rate represent? Well, it represents that dx dt, which we just wrote right here, okay? So we have a couple more variables. Okay, we have x of t, but don't we also have y of t right here? The height of our ladder is going to change at any given time. So we got that going on. What about this downward arrow that I drew from the top of the ladder? Well, just as the arrow we drew to the right of the base of the ladder was dx dt, this downward arrow is going to represent dy dt, the rate of change or the instantaneous rate of change of y of t. Okay, so this is all the information we've been given except for the fact that we know that it tells us x of t is equal to 12 feet. When it says that's basically this information right here. The rate is 5 feet per second. We got that down. So let's look at what it's asking. How fast is the top of the ladder sliding down the wall at this moment? What is it asking for? Think about that. Pause the video. All right, if you've given it a thought, what are we really asking to find in this problem? We're asking to find what is dy dt. So realize the basis of this problem, why they're called related rates, is we're given the rate dx dt, we're given this system of a ladder going against the wall, and we want to find how another variable, y, changes when our variable x is changing at a particular rate, okay? So how do you think we would do this? Think back to what we did in implicit differentiation. Remember that when we had an implicitly defined function, we could get a rate of change to pop out when we took the derivative of both sides of that function. So what we want to do in this case is we want to find an equation that relates all the variables that we've been given or are asked to find. So we want to find an equation that relates L, the length of the ladder, to Y, the height of the ladder, and X, the distance from the wall to the base of the ladder. So pause the video, see if you can think of an equation that relates all of those things. All right, if you've given it a shot, hopefully you came up with the Pythagorean theorem. So we have L squared is equal to x squared plus y squared. All right, so if we want dy dt to just pop out of this equation, what we want to do is take the derivative of that equation, and we will take the derivative with respect to time. In all related rates problems that we're going to deal with, time is always the independent variable, so you always differentiate with respect to time. So we take the derivative of L squared with respect to time, that's the derivative of one side, then do the derivative of the other side. All right, so practice your implicit differentiation skills right here. Do this derivative, try it right now, see what you get, pause the video. All right, if you've gone through and done this, what you'll get is that, well, if L is a constant, the derivative of a constant with respect to time, well, that's just going to be 0. So we end up getting 0 is equal to 2x dx dt plus 2y dy dt, like that, okay? So what can we do with all of this information, all right? Well, notice what have we been given in the problem? We were given dx dt, we were given x at that particular time, but we want to find dy dt, but we don't know why, okay? So we got to do something here to find what that variable y is going to be, and I got to find a way to extend the page. There we go. Because if I extend the page when the video is going on, the video stops. Thank you, Steve Jobs. You all knew that was coming. Okay, so what we got to do is we got to find y, okay? So how can we find y? Well, realize when we look at the original setup of the ladder, we had a right triangle that looked like this, okay? So how do we find y? We can say that 13 squared equals 12 squared plus y squared. 13 squared is 169, 12 squared is 144, so that means that 25 equals y squared, or 5 feet is equal to y. So now that we got that, we plug that back into our equation, and we get that 0 is equal to 2 times 12 times dx dt, which was 5. And actually, let me erase this because I just did a cardinal sin right there. I didn't keep track of my units, and that's going to be really hard for you guys if you don't do that, okay? So we got 0 is equal to 2 times 12 feet times dx dt, which is 5 feet per second. Then we add plus 2y was 5 feet dy dt. Okay, so that's all we're left with, and all we got to do now is solve for dy dt. Okay, so that just turns it into a very simple algebra problem. So if we go through that, we're going to end up that if we bring the 2 times 12 times 5 over to this side, what will that be? That'll be 120. So we'll get negative 120. If we multiply feet by feet per second, we get feet squared per second. And then we divide that by 10 feet, which is 2 times 5. that gives us dy dt, or by doing this, we will get dy dt equals negative 12 feet per second, okay? And so why does that give us a warm fuzzy when we see that? Well, it makes us happy because dy dt was going down. And so it makes sense that dy dt would be a negative number because that value y of t right here, as that ladder falls, that thing's going to shrink, okay? So that is how we solve a related rates problem. It may seem fairly cumbersome right about now, but once you do more of them, and the trick to these is practice, you will start to get better and better at them, okay? So let's find out another example of a related rates problem, which is related directly to this problem right here, okay? So now we got this. We got the same situation, but now look what's bolded, okay? I'm asking you a different question right now. So we just found out this, let's draw our picture again, okay? We got y of t is this distance, x of t is that distance, dy dt goes down, dx dt goes this way. We have our ladder at L equals 13 feet. From the last problem, we still had that x was equal to, what was that, 12 feet? We found that y was equal to 5 feet. We also found that dx dt was 5 feet per second, and dy dt was negative 12 feet per second. Oops. So try to read this problem real quick, and why don't you pause the video and see if you can apply the same kind of methods that we did before. Remember, we want to find an equation that relates all the areas, or I'm sorry, the equation that relates all of our variables together to find the rate at which the area of this triangle that's formed by the wall and the ladder is changing right here, okay? So first ask yourself before you pause the video, what are we trying to find, okay? At what rate is the area of the triangle formed by that changing? What we're asked to find is, we'll call it dA dt equals. That's what we want to find, okay? So find an equation that relates the area of a triangle to the variables that were given. Take the derivative of both sides and try to solve for dA dt. Try to do this on your own, see how you do. Pause the video. All right, if you gave this a shot, hopefully, and let me move over here because I know I'm going to have to extend the page. Hopefully, the equation you thought of was the equation for the area of a triangle. So we know that the area of a triangle is going to be 1/2 base times height. What's the base in this case? In this case, the base is x, and the height is y. Okay, so now take the derivative of both sides with respect to t. All right, so if you didn't get to this step, pause the video again and still just try to solve this for dA dt at this particular moment. Just give it a shot. All right, if you gave it a shot, when we take the derivative of the first side with respect to t, we just get dA dt. Now when we take the derivative of the second side, we're going to get the product rule that comes out of that. So that's going to be 1/2 the derivative of x with respect to t is dx dt times just y, then plus 1/2 x times the derivative of y with respect to t is dy dt. And in this one, this is just straight plug and chug to find this answer. We already have dA dt right there, so we just got to plug in all the values, all right? So we get dA dt is equal to 1/2 dx dt was 5 feet per second. Dy dt, or I'm sorry, y was equal to 5 feet. And then we had plus 1/2 x, which was 12 feet, and then dy dt, which was negative 12 feet per second, correct? That's what we got? Okay, cool. So we get that, so if we multiply all this out together, we're going to end up getting, this is 25 over 2 plus minus 144 over 2. These units will be given in, let's see, what do we get here? When we multiply, when we multiply feet per second by feet, we get feet squared, per second. Okay, so if we add these two things together, what'll this give us? That'll give us negative 119. Did I do that correctly? Yeah, I think so. Negative 119 over 2 feet squared per second. So let's take a step back, and what is this actually telling us about the problem? Well, this is saying that at this given moment in time, the area of this triangle is actually decreasing at that moment because it's negative, okay? And second of all, look at the units we got. We got feet squared per second. Well, if we're looking for dA dt, we're looking for the instantaneous rate of change of area with respect to time. If area is given in units of feet squared, it makes sense that the instantaneous rate of change of area with respect to time would be given in feet squared per second. So this gives us a warm fuzzy, and we're very happy. And it also kind of makes sense. You know, if the height of this ladder is, well, depending on what's going on, there might be times when the area of the ladder is increasing. There might be times when the area of the ladder is decreasing. I would say once the ladder, as it goes further and further down the wall, its area is going to start decreasing. So that kind of makes sense that we got a negative number right there. All right? So on to our third and final example. Try to give this one a shot. Now look, we've got, I'm going to go ahead and extend the page because we know we're going to need that page extension. Okay, so in this problem, now we are asked, at what rate is the angle formed by the ladder and the ground changing at this moment? Now, with none of my help drawing the pictures or anything, why don't you figure out what this is on your own? Try to give it a shot, pause the video. All right, if you've tried this, again, we're going to draw our picture right here. And we have y right there, dy dt, x is this distance, dx dt is going that way. We have the ladder of length 13 feet. And then what is the angle we are talking about? We are talking about this angle theta right there. Okay? So what are we being asked to find? We are being asked to find the rate that the angle formed by the ladder and the ground changing at that moment. So what we're trying to find is d theta dt, okay? That's what we want to find. So if you didn't get to this step and what that is, pause the video again, try to go further. Remember, we want to find an equation that relates that angle theta to the things that we have been given. All right? So if you give it a shot, the equation that we're going to use to relate this, there's actually several, but they're all going to be based upon trigonometric functions, okay? So we could say sine of theta is y over L. Cosine of theta is x over L. Tangent of theta is y over x. So pick whichever one you want to do. Let's just go ahead and say sine. Sine of theta is equal to y over L, okay? So now what do we do to that equation? We differentiate both sides with respect to t. So d dt sine theta is equal to d dt y over L, okay? So we take this derivative. Remember that when we do the right side, L is a constant. So that's the same as the constant 1 over L times the variable y. So when we take the derivative of the left side, we're going to get cosine of theta d theta dt. When we take the derivative of the right side, we're just going to get 1 over L dy dt. Okay, we know L, we know dy dt, we found that in the first problem. We want d theta dt, but we don't know theta, okay? So let's stop here for a second and say find theta. Well, we can do that again using trigonometry. If this is theta, and we know L at this moment is 13, y is 5, and this is 12, we can find theta that way. Again, pick whatever trig function you want to pick. It doesn't really matter. Let's just use tangent in this case. We have tangent of theta is equal to 5 over 12. So theta is the inverse tangent of 5 over 12. Okay, so there we go. We got theta. So if we plug all that stuff in, and kind of rearrange this equation right here, we can get that d theta dt will be equal to 1 over L, which is going to be 1 over 13 feet, times dy dt, which was negative 12 feet per second. And then all of that is going to be divided by cosine of theta. I thought we extended this page. Maybe we didn't. Or maybe it just unextended itself on us out of protest. So, okay, so if we divide this by cosine of theta, which will be cosine of the inverse tangent of 5 over 12, we will get some number, okay? I'm doing this in my head. I don't have a calculator on me right now, so I have no idea what that number is, but it's something, and it represents d theta dt, okay? But what's very interesting about this is that you'll notice d theta dt, when all is said and done, the units we will get will be in just 1 over seconds, okay? Remember that units or radians are unitless, so this is the equivalent to radians per second. And that makes sense because if theta is in an angular measure of radians, then d theta dt would be radians per second. Okay? So there you go. Those are 3 examples all in one problem of how we do related rates. And really, the trick to doing related rates problems, as I stated before, is just practice, 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 practice. So if you look in your books under the related rates chapter, go to the odd numbered problems in the back of that chapter, and I would highly suggest working on those. And since they're odd numbered, you have answers to them and you can check them. All right? But this is also present in your book. If you want kind of a strategy for solving related rates problems, this is what you should follow. And this is pretty much what we did with every problem we had. The first thing you do is you draw the picture and name the variables. Remember, the variables are the things that change with respect to time, and you also name your constants. Those are the things that will not change with respect to time. You're always going to use t for time and assume all variables are differential functions of time unless they're constants. Then they're just constants. So then you write down all the information you were given in a problem. Remember, we always did that once we drew our picture. Then you write down what you're asked to find in terms of those variables. Then you do, remember that big crucial step where you find the equation that relates the variables that you have to the variables that you want. And then after that, it's strictly mechanical. So really steps 1 through 4 are the hardest part. Step 5, where you just differentiate both sides with respect to time and then solve for what you're trying to find, that's just mechanics. It's the same skills we did in implicit differentiation. It's using the chain rule, and then it's just using algebra. Okay, so I would highly suggest maybe rewatching this video because related rates tends to be a really difficult topic. It's a long video, but it's very informative. And I'd also recommend that you really try to do those practice problems. We'll also do some practice problems in class, but like always, come in class ready to ask questions.